Hello and welcome back to Functional Analysis. And as always, many thanks to all the nice people that support me on Steady or PayPal. We've already reached part 18 in our course, and today we want to talk about compact operators. As the name suggests, this has something to do with the compact sets we've already studied. Therefore, recall that the idea of compactness has been to extend the notion of finiteness a little bit. A similar thing we will now do for operators. Here the analogon of finiteness would be linear operators between finite dimensional vector spaces. So let's look at an operator from Fn to Fm. On both sides we can just choose the normal Euclidean norm, the standard norm. However, everything I say now does not depend on a norm, it holds no matter which norm you choose here. The first step is not so hard to show. It tells us that the linear operator between finite dimensional norm spaces is always continuous. And of course, you already know continuous means the same as bounded for linear operators. In other words, the image of the unit ball under T is a bounded set. Now, this is a bounded set in our finite dimensional norm space Fm. And there you know, this is one half of the things you need for being compact. However, the second ingredient we just get when we form the closure of this set. This means that we just can use a bar over the set. And then we get a set that is always compact in Fm. With this, essentially you now know what a compact operator is. When we look at the image of the unit ball and form the closure, and this set is compact, we speak of a compact operator. Of course, this always holds in this case, but not in general. In order to see that, let's consider the identity operator in LP. Of course, identity operator just means we take a sequence X and send it to itself. Therefore, calculating the image of the unit ball is not so hard, it stays the unit ball. Now we are interested in the closure of the set, so we use the bars again. So what you have on the right hand side is just a closed unit ball in LP. And there we know from the last video, it's closed and bounded, but not compact. Hence we have something here we would not call a compact operator, because the image is just too large in this case. So you should always remember, compact operators is what we get when we extend the finite dimensional operators here a little bit. Okay, then let's write down the formal definition. So we need two normed spaces, and often there will be Banach spaces. Then a bounded linear operator T from X to Y is called compact, if we have the thing we discussed before, that this set here is compact in Y. Therefore, in the case that Y is a finite dimensional norm space, this here is nothing special. However, in the infinite dimensional case, it really is. Hence, I would suggest that we now look at a common example. Let's look at an integral operator defined for the continuous functions. So it should take a function defined from 0 to 1 and send that to another function in the same space. And as often, the space of continuous functions should carry the supremum norm. So what we can do is apply the operator t to a function f, and then we get out a new function. Hence we can look what the function does at a given point s, where s comes from the unit interval. Now the number that comes out here should be given by an integral from 0 to 1, where we have the function f involved, but also a fixed function k. And this function should get the variable s and also the integration variable t. So we have a function with two variables, and for us it should be also a continuous function. So we have it from c defined on the unit interval times the unit interval. Now since the function k goes into the definition of t, I put it into the index here. Okay, then let's check if tk is indeed a compact operator. An important fact we will need here is that the function k is defined on a compact set, so it's not just continuous, it's uniformly continuous. To refresh your memory, let's write down what this exactly means. For all epsilon greater 0, there exists a delta greater 0, such that for all points we put in, and now we need two variables, and for them it should hold if the distance is less than delta, the distance of the images should be less than epsilon. On the left hand side we measure the distance with the Euclidean norm in R2, and on the right hand side we measure it with the Euclidean norm in R1, which is the absolute value. Why we need the uniform continuity here, we see in a moment. The first step we have to do when we see such an integral operator is to check if this integral defines indeed a continuous function. Simply because otherwise the operator wouldn't be well defined. It really should map continuous functions to continuous functions. Checking the continuity then means we look at the difference of the images when we put in different points. So this should be small when the points S1 and S2 are close together. Therefore, we first calculate and then we can look what happens. Now the first thing you should see here is that we can put that into one integral. So use some parentheses here and delete this integral here. Then of course we pull in the absolute value, then we get an inequality. And with this we have everything we need, because this one here is less than the supremum norm of f, and this one by the uniform continuity of k can be as small as we want. And exactly this is what we should formally write in front of the whole calculation. So for a given epsilon greater than 0, we choose the delta in such a way that this whole thing holds. Therefore we can choose S1, S2 from the unit interval such that the distance is less than delta. For this S1, S2 here and the same t on both sides, we can apply what we know, that this is less than epsilon. By using also that this one is less than the supremum norm, we are finished with the whole integral. It's simply less than epsilon times the supremum norm. And because the supremum norm of f is just a constant in the whole calculation, we now know that this function is indeed continuous. So we can note our operator as written as here is well defined. However, our calculation here shows us even more. If we define the set A as the image of the unit ball, then we see by this whole estimate here that the set A is uniformly equicontinuous. If you don't know what this means anymore, let's write it down again. It just means that for all epsilon greater 0 there exists a delta, such that for all S1, S2 and all G in A we have the uniform continuity implication here. From the definition of the last video I only had to change some names. I used the name G for the function here because we already had a function f. And of course we needed the names S1, S2 for the variables. However, what you should see is that this one is the definition of A being uniformly equicontinuous, and it's the same thing as we have written here. In other words, with the calculation above, we have proven that A is indeed uniformly equicontinuous. At this point you might already guess that we want to apply the Spectral theorem here. Therefore, another step we have to do is showing that the whole set is bounded, or in other words, that the operator is bounded. Hence, let's calculate the operator norm. So we have the supremum of all the norms of the images, where f has norm 1. By the definition of the supremum norm, this is the supremum over all s, where we calculate the absolute value of the integral. As often we can just pull in the absolute value into the integral and get an inequality out. And with this we are almost finished, because the last part here is less or equal than the supremum norm of f. And this is by assumption just 1. This means that we don't need the outer supremum anymore and can just write down everything is less or equal than this integral. However, this is also less or equal than the supremum norm of our function k. As often it's not important what the number here is exactly, it's only important that it is constant. Because then we know that tk is a bounded operator. And now finally comes our conclusion, we can apply Arzela Ascoli. This said, the image of the unit ball is uniformly equicontinuous and bounded. Therefore, both things also hold for the closure of the set, and by Arzela Ascoli we now have a compact set. And by our definition, we also know tk, the integral operator, is a compact operator. So you see, this was a long example, but it is a standard example for a compact operator. Of course, we will talk about compact operators in later videos even more. Therefore, as always, I hope I see you there. Bye!